Good afternoon, everyone. I'm extremely happy to introduce today's speaker, Professor Josh Warren from Yale School of Public Health. Before a more official introduction, I would like to share with you a little more of my personal experience. I took the first course on Bayesian statistics with him when I did my master at Yale University. His teaching was so clear and engaging that I decided that I would like to do research on Bayesian inference since then. And we have also collaborated on 2 research projects, both on spatial temporal models for environmental epidemiology data. I learned a lot of practical skills from Professor Warren, and more importantly, those delightful experiences motivated me to pursue a PhD degree further, which led me to the BSU here. Yeah, so today I'm super happy that he finally visit our unit and visit Cambridge. Welcome.
Thank you so much.
Okay, now comes a more official introduction. So Professor Josh Warren is currently an associate professor in the Department of Biostatistics at Yale School of Public Health. His research involves statistical methods in public health with an emphasis on health problems. Much of his work involves introducing spatial and spatial temporal models in the Bayesian setting to learn more about associations between environmental exposures, such as air pollution, and various health outcomes, such as low birth weight. He also has interest in developing and applying spatial temporal models in collaborative settings, such as in infectious disease epidemiology and geography. Now, without any further ado, I will pass the mic to Professor Warren.
Thank you so much for the really kind introduction. It's great to see you again after so long. It was a nice afternoon spent with some of the faculty getting to meet you and lunch. And so I really appreciate the opportunity to be here and to be speaking to you. So today I'm going to talk a little bit about some of work we've been doing in the exposure environmental health space, statistical methods here. But as the introduction kind of mentioned, I've since COVID have been really engaged in the infectious disease epidemiology. So I do a lot of spatial statistics, space-time, disease spread, and understanding kind of what's going to happen next in terms of lots of different diseases, which I'm not an expert on, but I kind of learned enough to help with some analyses. I'm part of a larger modeling unit. I'm in the Department of Biostats, but there is a public health modeling unit at the School of Public Health, where we're epidemiologists, health policy, causal inference, lots of different faculties sit together. And if you have interest in like any of these types of issues with infectious disease or environment, climate change, we're doing a lot of this, feel free to reach out. We often have visitors who come and stay for a month or 2 at a time and kind of do research rotations. So please, if you see something and if you are later Googling and see someone else in the unit who is interesting to you, I can definitely make connections and things like this. We're always happy to have people who are interested in similar problems, which it sounds like here, a lot of overlapping interest in some of these problems. But today, I'm really going to be focused on an air pollution and stillbirth application, but an interesting, I think, methodological issue that we've experienced recently. So a little background about the world we're working in here. So environmental exposure modeling. So health studies obviously want to estimate associations between environmental exposures and adverse health outcomes. So I deal a lot with pregnancy outcomes, but recently we've been thinking about cancer, different forms of cancer, lots of kind of cardiovascular outcomes as well. And a fundamental challenge here is that these analyses require exposures to be linked to each observation in a data set. So I'm thinking, if you're thinking about a pregnancy study, a row of your data would be an individual who gave birth at some point in your study period, and you want to know what they experienced. In this case, we're going to be talking about one kind of exposure during a time frame, but you can think of like maybe daily exposures throughout the course of pregnancy, for example. It's a relatively simple idea. We want to link what you were exposed to your outcome. But unfortunately, data are not collected like this, at least commonly in the US. So exposure data are typically collected by fixed monitors that are located across the US, that are there for not health study purposes. So they're not optimized for our use, but they're optimized for more policy implications by the EPA. So people live not at the monitors oftentimes, unfortunately. So we're left with this kind of spatial misalignment issue, which is how a lot of Bayesians and environmental health statisticians have gotten involved in this world. So because these exposure data are not available at every location and time, predictions from a first stage model are often used to fill in these space-time gaps. And so recently, in the last few years, several advanced and machine learning methods have been introduced, which try to fill in these gaps. And so we're using satellite imagery, the chemists have a whole world of producing these deterministic output of at a really fine residential or location, 1 kilometer grids, for example. So they're doing some deterministic things of producing air pollution estimates that are completely full in space and time. And we're looking to model these as a function of what we consider to be the unbiased version that collected by a monitor, for example. So lots of methods and many, an important aspect here is that many have been introduced within the Bayesian framework. That's going to be important for moving forward here. And so here is this case study that we'll talk about a little later on. Here's the US state of New Jersey, kind of New York here and Philadelphia, somewhere around here. The blue represent active EPA air pollution monitoring stations. These are ones that collect information on PM 2.5 on a daily or semi-daily basis. And on the grid here represents where chemists have created a more complete in space and time deterministic product estimates of PM 2.5. And so through some modeling procedure, there's lots of ways to kind of include this auxiliary information to improve the space-time coverage, but you usually end up getting something like this. So this is for a particular day of our study. We have imputed kind of through some spatial modeling, which we'll talk about a little bit later on, the surface. And so now if you live here or here or here, and we're trying to link you in space and time, we have something we can kind of hang our hat on and say, you're more likely, instead of just like a closest monitor calculation, which is used often in EPI. So modeling, and then people release these products. There are lots of them now. They release these point estimates typically on their website, and then you can use them for your EPI study. However, so these Bayesian methods yield samples from the exposure posterior predictive distribution for every observation. So on that map that we just showed, there's not only a point estimate there, though, right? There's a distribution of, that characterizes the uncertainty, the shape, the spread of what we know about exposure in that location. So how do you fully incorporate this information, so not only the central tendency, but also the uncertainty, into subsequent health analysis? It's kind of still an open and important question for conducting accurate inference on these associations of interest. Because intuitively, we would say that health observations linked to exposure with higher uncertainty should contribute possibly less to the overall health effect estimate. So previous studies often ignore this uncertainty entirely, and that's not a knock on what they're doing, but it's often out of necessity. Like the EPA releases a really nice yearly and daily estimate of ozone and PM 2.5, but they give you only the point estimates. They've actually started giving you posterior standard deviations as well, which is a good step. So oftentimes you are only left with point estimates to use. And so in the absence of more, I can see how this happens. But so overly simplistic summaries of posterior predictive distributions, or implement some rather ad hoc approaches to account for this uncertainty. So back to our case study in New Jersey. So this is, these are the modeled and predicted daily PM 2.5, maximum PM 2.5 estimates or predictions. So these are the posterior medians of the posterior predicted distribution on every day from 2011 to 2016. And just to understand, so for any one day, if you look, underlying one of these points on this map or on this time series plot is a distribution that we're basically saying we're using the posterior median to stand for. So I want to be able to characterize this uncertainty and bring it into the health analysis in some computationally feasible and kind of helpful way. So this is a good point, I think, to talk about what, if I was just being introduced to this problem, this is the first time I had heard of this issue, I would say, why not just do everything in one big hierarchical Bayesian approach, in a joint modeling approach, if you will? So have the exposure and health modeling kind of in the same framework. I still think it's probably the gold standard. It's the thing that you should set out to probably try to do, as opposed to breaking up these stages. But it's becoming computationally pretty complex to do so. the health, or excuse me, the environmental exposure modeling is typically, well, it's getting much more complicated. And just bigger domains, bigger spatial domains, bigger years. And then the health modeling on the other end is no longer just, in a lot of cases, your typical, EPI style logistic regression analysis with some covariates and then a predictor of exposure. They're becoming more complicated as well. So the idea of putting both of these together and doing this kind of spatial temporal imputation in the same framework is a nice idea, but it's at this point the two-stage approach may be a more computationally feasible thing to do. There's also a conceptual argument that I'm not sure if I fully kind of have thought out all the way, but there's this idea of the cut of feedback in these models. So in a full joint model, the health data would be providing some insights into the air pollution data. And there are some people who do not appreciate that feature of the joint model. So they like the idea of things kind of moving in one direction, like first stage health exposure modeling feeds into the health model. Doesn't necessarily bother me as much, but again, I haven't thought about it as much maybe. All right, so questions of interest in this particular project was, if you had done this modeling yourself, your exposure modeling, you've had posterior predictive samples from a first stage exposure model, what's the best way to include this information in your health model? What are the implications of using existing approaches? So I really wanted to also understand what had been done before and what are the implications here. And I guess, can we develop something computationally tractable that people will actually have the potential to use in their own work? So, and for this, because I work in public health, I work with I've seen different health outcomes, and they often follow you have some kind of Gaussian response, possibly you have some binary yes or no, and then you have some Poisson counts for disease counts, for example, or negative binomial. So if we could cover all three of these categories, we feel like it would be a pretty usable method across multiple problems. So what we've proposed to do is use Gaussian kernel density estimation to define exposure prior distributions for the health outcome analysis. And the framework allows for improved characterization of the shape and uncertainty of the exposure posterior predictives, while also still maintaining some computational benefits. And we go through a simulation study that shows this approach leads to improved inference under different settings. And we're going to use it to investigate the exposure, top population level exposure to PM and stillbirth in a time series analysis. Also not mentioned here is it has some really conceptual, when you get into the full conditionals, as we do a little later, you'll see it has some good connections with what's been done before and these other approaches. It's like a nice bridge between two approaches that I think is intuitively nice, at least. So to set the stage here, we're not going to talk about the exposure model, but you could apply any Bayesian exposure model that you were interested in, and you're left with this Z-star matrix. And so on the rows here are the individuals. So you can think you have n individuals in your study or n time points if you're doing a time series analysis, and you've collected m posterior samples from their posterior predictive distribution, their exposure. And so we generally assume, like maybe you've done this in an MCMC way. So you've done your thinning and you've done things to ensure we're making the assumption that there's independence across the columns here. So we have like IID samples from this posterior predictive, but there may be correlation across the rows. So the people here, like if they're spatially located, if you and I are closer together, there may be a correlation in our exposure. So there may be correlation this way, but there's independence this way. This is important for the simulation study aspect. Also, a lot of the exposure modeling, sometimes they actually simulate from the joint posterior predictive distribution, which would kind of induce correlation here. Other times they're doing it kind of on a point-by-point basis, which would mean independence in both directions. But we're allowing for a more general setup here. So this is where our starting point is for the health analysis. All right, the stage 2 health outcome. All right, so now we're going to focus on a basic EPI style study here. We're going to be very general at this point with what we're talking about. So we have some conditionally independent outcome yi, follows some distribution. It could be Gaussian, it could be Bernoulli or binomial, it could be negative binomial, etc. It has some link function where we have an offset term, this OI. We have some predictors, confounders, covariates. So if you're thinking pregnancy outcomes, it may be demographics, race, ethnicity, it could be age, things like this. And then what we really care about is this ZI theta. So ZI is the true but unobserved kind of exposure that person I or time period I experienced. And theta is the thing that, you exponentiate it, we have an odds ratio, and this is what we would be the primary output from such a study. It's what we're really interested in doing and learning about. So the question is, given that Z star from the stage 1, the posterior predictive samples, how exactly do we inform about theta here, and what kind of prior distribution do we build for ZI? So before we jump into what we've proposed, let's talk about what's done currently. The most common, if you kind of look through the literature, especially in the epi world, is this plug-in idea. So the plug-in exposures are really simple computationally and popular in past work. So you replace ZI in your regression model here by some function of one of the rows of the posterior of the Z star matrix. So basically you could take the column, you could take the mean of a row, which is posterior mean or posterior median, mode, whatever makes most sense for your context. Usually it's the posterior mean is what's reported by some of these products. And so you're just literally plugging in this Z hat into your regression model and pushing forward as if that was your exposure. And yeah, so this obviously ignores prediction uncertainty from that stage 1 entirely. Another approach that's been used in the literature is this multiple imputation. And the idea is that for every each of your M columns, you run the analysis, one time. So M analyses have been run in total, and then kind of putting together the posterior estimates of theta from all of those model fits. So you're just cycling through these different columns of exposure because, I guess in this world, any of them are as likely as any of the others. So unfortunately, in this setting, MI is known to produce biased effect estimates because it doesn't condition on the health outcome. But there's an approach coming up, the discrete uniform approach, which tries to improve upon this. There's also can be kind of computationally demanding if you have 10,000 posterior samples and you need to run a really high level kind of MCMC model in your health analysis 10,000 times, that can be problematic. So this was introduced more recently, the multiple imputation approximation. And every iteration of your MCMC algorithm, it swaps out a different column of Z star. So it doesn't condition on just one, it's just cycling randomly through Z star with replacement. So you're kind of working that uncertainty in. It feels rather ad hoc to me. I haven't seen like it written out as produces actual samples from the stationary posterior distribution of interest, but it is definitely much quicker, obviously, because it only requires one run of your health model. This is an approach by Roger Pang and Howard Chang several years ago now. And this one is, I mean, initially I liked this one a lot. I thought it made more sense than the other two. It's the discrete uniform prior. So it says that your column, so this Z is now bold. I don't know if you can tell it's bold here, but I'm talking about the entire vector Z of exposures from the N individuals. You assume that one of those columns is kind of the true here, the red Z, the true but unobserved exposure. So you say, we don't know which one it is. So a priori, we say it could be any of them with equal probability. So 1 over M. And the nice thing here is that it's always, you have conjugacy no matter what, because you have this discrete prior distribution. So the posterior or the full conditional distribution has a really easy to sample from form. So it's nice here. It makes a likely unrealistic assumption that the true vector is in your matrix. So you're basically confined to what you observe in those posterior predictive samples. It's basically the search for the most realistic or the most reasonable vector of exposures. It also does a nice job of characterizing the kind of correlation because it's looking column by column. So any correlations that's contained in the columns is kind of automatically carried through. So it's a health data driven version of the multiple imputation and MIA. So you only have to do it, fit it one time, and it has this discrete prior, which is nice. Another really commonly used approach is let's just focus on the kind of the mean and the variance or covariance of your sample of your matrix Z star. So let's just summarize them with the means or medians and then the variance covariance matrix So you say now the Z has this prior distribution, it's multivariate normal, centered at the row means or row medians and variance covariance matrix. And this is nice because now you're no longer restricted to one of the columns that you've observed in Z star. So it can differ from that. You are technically still capturing the correlation within the columns here. And yeah, and so it allows you to kind of move away from the matrix some. But the downside is it obviously assumes normality and only relies on summaries of the posterior predictive samples. So if you see here, only kind of summaries are included. The actual raw posterior predictive samples themselves are not in this formation. Very, very recently, there was an approximation to this approach called sparse multivariate normal. It's an approximation to the full multivariate normal, where it has the same form as before, but it replaces the variance covariance matrix with something pretty sparse. So this Q inverse, Vecchia approximation. Yeah, so this is trying to do exactly what multivariate normal does, but it's much quicker, at least according to the paper that recently came out. So it's a nice kind of computational improvement because it's such a sparse matrix here. All right, just so we don't, we are focused on really only on the Bayesian options here, but there is some work that has been done in the frequentist world, a lot with bootstraps and kind of the SIMEX procedure. But the parametric bootstrap fits a two-stage model, estimates the parameters, and then starts generating and simulating exposures and health outcomes from the fitted model and reanalyzing. It repeats this many times. The non-parametric bootstrap is actually subsampling from the exposure and the health data, and in a way that's kind of trying to do this. So these can be really good, especially if you can fit your models quickly. So if you have to do it again and again. SIMEX was also extended to kind of this spatial exposure setting for very similar reasons here. So there are non-Bayesian things happening, just to give a more complete picture here. I'm sure I've missed some important developments here, though. All right, so what have we suggested to do? We're going to start with the univariate version here, just because it was like simpler conceptually to me to start here. If I wanted to specify a prior distribution for person I's true exposure, and I really didn't want to rely on only summaries of the distribution, and I didn't want to assume that it was one of the ones that I observed, like discrete uniform, then a nice hybrid approach is to make it a mixture of normal distributions where it's centered at the actual posterior predictive samples. So these are, you're using however many samples you collected, M here, and you're centering each of these at the, the actual observed PPD sample. The H here represents this bandwidth variable that controls the level of smoothness of the density function, and this is estimated in our work just with some standard kind of kernel density estimation functions and methods. So nothing special about the H function here. You could definitely go into a rabbit hole about how to best estimate these, but that wasn't our focus here. But the idea here is now we have this distribution that's possibly, can have multiple modes, it can have heavy tails, whatever the shape is, but it also uses the actual Z stars. And I'll show you why that's interesting when we get into the full conditionals. But it represents a nice hybrid approach between discrete uniform and multivariate normal that I think can explain why some of the improvements that we see in the simulation study. So obviously, once we wrote this down, and so the mixture of normals is really helpful for conjugacy, obviously. So a lot of what we can do with this approach is dependent on the likelihood, and we can show for several different likelihoods that we can get something that has kind of an exponential structure that really pairs nicely with this. So once we wrote it down in this way, we were really excited that conjugacy would not be lost with this more flexible approach at characterizing uncertainty. So conjugacy is a big thing. So then we thought about multivariate Gaussian because clearly we want to. This is assuming independence across the rows here, which we don't necessarily believe is true. The multivariate version proved difficult, and the reason is this H. This H is kind of describing the variance covariance between your n rows here. And so we needed a method for kernel density estimation, multivariate kernel density estimation, for estimating this H. And there are several methods, but a lot of them are keyed in on, they call large dimensionality, like between 4 and 50. And in these data sets, we're generally dealing with, tens of thousands, hundreds of thousands, even millions of individuals. So to define this matrix proved to be difficult, at least in our study. I think it's something we should think about for in more detail, but it did not seem to work well with the type of approach we use, which is kind of based on the sample covariance matrix. So that's just it would be really conceptually nice. You still get conjugacy, still have a lot of nice features here, a mixture of multivariate normals instead of a mixture of normals. But there we hit some stumbling points here. Just to get to kind of stabilize us here in what we're doing, a plug-in approach would basically take this posterior predictor distribution and say this person's exposure was whatever it is, 17 or 18. The multivariate normal in the blue would have this shape, and then our kind of kernel density estimator would kind of maybe better characterize the peak and have some heavier tail here. So this is what's happening, I guess, just conceptually, but it's not all based on, well, yeah, so now to the full conditionals where we'll see what I particularly liked about the approach. So what computation across all these methods, we've basically been able to kind of consolidate a lot of different likelihoods. So Gaussian, Bernoulli with a logit or binomial with a logit link function, and then negative binomial with actually a logit link function on the probability. And under these functions and likelihoods, you can actually show that all the likelihood contribution from your health data will come through the model and is proportional to this exponential term, where the sigma, the omega and the y tilde are different for based on what your link function is and your likelihood. But the point is, this works really nicely with our kernel density estimation prior distribution form because z is sitting there in an exponential, and we have lots of hope for conjugacy. So that's part one, is that we're able to handle a lot of different likelihood choices. And this helps because we've created an R package where you can choose which one you're interested in. But let's talk about computing discrete uniform first, because this is a good starting point. So discrete uniform, it had that nice discrete prior. And basically, when you think about what the full conditional distribution is, you're asking, what is the probability z equals some column in your big Z star matrix, given the data and the rest of the parameters. And we can show that it looks a lot like just a likelihood ratio test. You're basically plugging in different Z stars into this exponential term and dividing by the sum of all those. And so what this means is you're consistently choosing ones that have higher probabilities here. And so you're kind of, unlike multiple imputation, which randomly cycles through all of them or does them in a kind of random sampling in the multiple imputation approximation version, this one's focusing in on ones that tend to agree more with the health response. So this is nice. Again, the issue is that you're stuck with one of those columns. So if none of the columns accurately represent the true exposure, you're kind of in a world where you're choosing the best one, but maybe the best one among a bunch of garbage columns. So that's potentially the drawback here. However, multivariate normal allows you to escape that matrix because its full conditional distribution update means you're drawing the true z from a multivariate normal distribution, which is a function of the variance covariance matrix of Z star, and also the mean or the median, whatever you use here to summarize the central tendency. So this is nice, but you're only using these first and second moments of the distribution. You're not characterizing possibly heavier tails or multiple modes, whatever it might be. And you would obviously replace sigma hat with Q for the sparse version. So we have these two methods that are widely used. And what does when we go to compute the univariate version, for example, so there's actually two steps. Because we have this discrete kind of mixture of normals prior distribution, it turns out that the posterior is also a mixture of normals. So to update such a thing, we have like a two-step process here. The first is you're computing these CIJs, which are functions of the health response for this person, but also every individual posterior predictive distribution kind of output sample here. So you're cycling through all columns, all M columns, just like you did with discrete uniform. You're choosing first kind of the Z star that, or one of a more probable Z star. So similar to discrete uniform, the first step here is you're centering your distribution on something in one of these columns of Z star that seems appropriate. But the next part is you're actually updating based on that selected value. So that selected value becomes kind of the anchor for the mean of the distribution that you sample from, which is a normal distribution. So you choose the location, and then Zi is next drawn from a normal distribution whose mean depends on that one that was selected. So this is an approach where with DU, you're kind of choosing a probable column, but then you're also able to escape the columns by drawing from a normal distribution. So unlike using just the summary statistics from Z star, you're actually using individual draws or individual columns in the case of the multivariate version. And so we think the multivariate version should be able to better characterize this kind of correlation if H can be estimated well. But again, we've struggled there. All right. So given this kind of, we were excited about this approach. It seemed to work computationally, and we liked it conceptually, so we wanted to test it. We tried to set out for a relatively simple simulation study here, where we have some response that's just driven by the ZI, the true ZI, and some health effect theta with some normal error around it, with 250 people to keep things running quickly here. So the first step is we simulated some Z star matrices based on different settings. We'll talk about in just a second, but 250 rows and 1,000 posterior IID posterior predictive samples were simulated. The true Z, the red Z, was the 1001th column. So basically, it's just a random selection of what would have been in the Z star matrix, but it's not included in Z star. So the true Z is not a part of the one you observed. Very much like if you're doing your actual exposure modeling, you don't necessarily think one of the columns is the exact exposure that everyone experienced. So we're trying to be as realistic as possible here. But we're also making this assumption that your exposure model is like you've got the right kind of process going that could have produced the true Z. We test that sensitivity later on, but for now, this is where we start. We test both when theta is null and theta is equal to 1. And how do we talk about actually simulating these Z stars? Well, we wanted to test when things were very kind of bell-shaped, where we wouldn't think the KDE approaches would have much advantage, but also when there's more severe kind of longer tails that you may see with like PM 2.5, for example, and kind of correlation. So we think about correlation in terms of spatial correlation in this context, where we make it big and small, uncorrelated and correlated. We think about symmetric or skewed versions, and we think about how kind of spread out these distributions are from each other. Are they all kind of, is there a lot of uncertainty with respect to the signal or not? So we try to kind of go across many different settings here to test these methods. To give you a sense of what this looks like for a few different data sets, this would be like uncorrelated and symmetric. This would be kind of skewed and uncorrelated, and then you can see the spatial correlation coming into play with the symmetric and the skewed as well. So we're testing these 4 settings. We simulate 500 data sets from each combination. Each method is applied and theta is estimated. And we really wanted, at the end of the day, what we care about is theta here. So we look at the bias and mean squared error of the posterior mean estimator. We're also very interested in the empirical coverage. We have this sense that, for example, the plug-in process should not yield very good coverage intervals, credible intervals, because it's ignoring that uncertainty. We wanted to see if that was true. So let's go to the results from the case where there was a signal. And I guess some interesting things. Well, first of all, you can see the kind of overwhelming, pretty good performance of the univariate kernel density estimation. I don't even show MKDE. It pretty much resembled discrete uniform. I'll show you on the next slide. But I guess some interesting facts here, or interesting takeaways from us, is that some things we knew, and when there's no skewness, the plug-in procedure does pretty well. Like the bias is fairly low, but as soon as there's skewness, that point estimate gets drug out, and you get further away from the true exposure. So I guess moving forward, it's good to at least understand and take a look at what these posterior predictive distributions look like to see if this is a safe approach or not. And maybe switching to the posterior median instead of mean, for example, to kind of limit the impact of some heavier tails. Similarly, the mean squared error. But the coverage for these approaches was fairly good overall. Let's see, the multiple imputation and multiple imputation approximation perform very similarly to each other, but pretty poorly overall. You see really high bias in every situation, really high MSE, et cetera. Barely ever covered the true parameter of interest. And discrete uniform, while performing slightly better, kind of had similar behavior to these two. So while I thought conceptually discrete uniform would help us kind of key in on a few different columns that were strong candidates, it seemed to be still yielding too much spread across and resembling this kind of multiple imputation approach. So there was too much posterior probabilities on all the columns. So it was jumping around more than I would have guessed. And univariate kernel density estimation seems to do well across many different of these different settings. To give you a visual sense of what this estimation looks like, these are the 4 different settings. So unskewed, unbiased, skewed, unbiased, and then further here. And you can see this UKDE, regardless of setting, it's kind of around the truth with smaller spread, while the plug-in approach has lots of uncertainty, which is why those credible intervals didn't suffer as much. And the multivariate normal, which we thought would perform well, tends to perform well, but every once in a while, in certain settings, it would be relatively biased and kind of miss the mark. And the multiple imputation approaches, you can see, always were kind of attenuating towards the null here, kind of pulling everything towards the null. Discrete uniform tried to do better, so conceptually it made sense what they were doing, but I would have hoped or thought that discrete uniform maybe pushed up further here. But that was consistent behavior for the multiple imputation approaches across the different settings. So we found similar findings for these different settings. We did a sensitivity analysis where we pretended like Z was not a candidate from Z star. So we added some additional noise to the true Z. And we found, so basically a misspecified exposure model. We found very similar performance across the methods. So we're happy with that performance. So now to the case study here, we wanted to apply this in practice and see what's going on, if we can discern any differences between the methods and real data. So we focused on stillbirth in New Jersey. New Jersey, at least in the US terms, is a fairly highly polluted area, being close to New York City. There's some elements there of air pollution, but then Philly on the other side. So New Jersey has a kind of a bad reputation for high air pollution in the States. And so we focused on, in particular, these 3 closest ones to New York, closest counties. And the outcome was singleton deaths and births with clinical estimated gestational age greater than 20 weeks, and that had a fetal death on or after 20 weeks that was defined as a stillbirth. So before 20 weeks, not a stillbirth. So yeah, what we focused on here is a time series analysis where we use daily lagged maximum PM2.5 concentrations to explain variability in stillbirth counts. So is there an association between kind of population level air pollution levels and stillbirth counts kind of in aggregate in New Jersey across the time frame we were thinking about? So here are the counties we were focused on. Here's the proportion of stillbirths in the state. So on 71% of days, there are no stillbirths. So this is a pretty rare outcome, but there is some variability. I can't tell if there's seasonality, but there is definitely some variability in across New Jersey, at least in these 3 counties. So stage 1, we had to start from the ground up here to do this accurately. To implement our method, we needed posterior predictive samples from some exposure model. So we went out and we tried to define our own exposure model here. So we have ZST, which is the air pollution monitoring value at spatial location S during time T on day T. And we model it as a function of an intercept, a slope, and what is the slope kind of talking about? It's the CMAC or the chemist model output. So in that first slide where we had the gray grid of all those outputs, we basically link the closest air pollution monitor with the closest grid cell, and we use that to regress, to run this regression and hopefully allow us to impute for places where we don't have air pollution monitors. And so The key here is, though, that the chemists do well in some parts of the country and some parts of the state and do not so well in others. So we need a spatially and temporally varying regression parameter model to kind of capture this variability. Sometimes it's unbiased, sometimes it's more biased or less biased across day and space. So we model these slopes and intercepts as a function really simply of latitude, longitude, their interaction, and then some time elements, some kind of smooth splines here. So this is like a separable space-time process, but it's fairly flexible and allows us to account for this variability in a number of different ways. It's probably not the exact model we fit if we were only thinking about exposure as the outcome here. There's no interaction between space and time, for example. But it does a nice job of getting, of producing kind of predictions that we feel are pretty accurate. So here again are the posterior means or posterior medians of maximum PM 2.5 across the 3 counties. And for one given day here, we show what the posterior distribution looks like, which has slightly heavy tail, which is probably driven by the fact that we're using the maximum, but also PM 2.5 tends to have a heavier tail. So this is not completely surprising to us. All right, for the health model, we're modeling the number of stillbirths on any given day. And so we're using a negative binomial to account for overdispersion potentially. And here, I know if you've used negative binomial regression before, you're probably not used to seeing it written as a logit. You're used to seeing like R over R plus lambda. But this gives you very similar interpretations. If you exponentiate the regression parameters, you still get like a rate ratio kind of interpretation. But this jives really well with our conjugacy, our modeling here. So what we model this as a function of some offset. So the total number of births, a day of week effect, because a lot of these are kind of planned in the US. So like on the weekends, for example, there could be an effect versus weekday as a function of just time. So a large scale time trend across multiple years here, minimum temperature, maximum temperature. And then what we really care about is exposure at some lag time L. And this theta is what we want to learn about. So as exposure goes up, does the rate of stillbirths increase? So we applied several models. We actually went ahead based on a reviewer recommendation and did the joint approach too, which was very slow and painful to do. But this is if you did all of those steps in one framework, this is what you would get. So at lag 2, maybe elevated but not significant. At lag 3, we actually see an increased relative risk, so increased air pollution exposure 3 days prior to delivery tends to increase the number of stillbirths on average in this analysis. The plug-in approach actually does fairly consistently here. This is a win for a lot of the epi studies that have come before us. And really interestingly, for the multiple imputation approximation, you can see that same behavior that we saw in the simulation study, like this thing has been being pulled towards the null. So this was comforting to find this in both worlds, I think. And discrete uniform pretty much agrees with what we saw as well. So it's pulled down, but maybe not as high as multiple imputation. So you can see both of these kind of performing, which means I feel like our simulation study was designed well so that we were able to capture these two effects as well. And then the multivariate normal and then the univariate kernel density estimation approach look fairly similar here. This has slightly smaller uncertainty for what it's worth, but the multivariate kernel density estimation not shown here looks a lot like discrete uniform. So whatever it's doing is it's closer to this than one of these. So we felt good about the method. We think we found some interesting signal here 3 days before, but we're thinking through this also in kind of a causal landscape. So we tried to over adjust for like time and trends and meteorology, other things. But as a final test, we basically took our data frame and we swapped all the dates. So now day 1 was day 7, and like everything was just mixed up. And so we were thinking if the signal remained here, there was some other confounding variable that we were missing. And what we saw is under these swapped or shuffled exposures, you get a null effect, pretty consistent null effect throughout. So overall, we're more leaning towards like there's an association worth mentioning here in these data at least. And once we're seeing these results, we're going back through the epi literature. We're finding so what we found is that elevated exposure to maximum 24-hour average PM. 3 days prior was associated with elevated risk of stillbirth, a relative risk of 1.19 per IQR increase. And this was supported by some other epi studies that found 3 days before delivery, odds ratio of 1.28 per IQR increase. Another one, the carbon monoxide, 2 days before pregnancy, 1.2. So in the same order of magnitude, same kind of unit scale here. And performance of the methods resemble findings from the simulation study. So in conclusion here, we think this is potentially a promising approach for fully characterizing uncertainty in the first stage exposure modeling using actual posterior predictive samples. The simulation results suggest it generally leads to improved estimation of the association of interest. New Jersey, we found an interesting signal 3 days prior to delivery with increased risk of stillbirth. And what we're currently interested in is more complex health analyses. So this is more of a traditional epi style analysis, but we do in our group a lot of what we call critical window estimation, which is time varying exposures. So like pregnancy and like what you were experiencing each day or each week during your pregnancy, kind of jointly modeling that effect. And so can something similar be used in that more high dimensional exposure setting? We haven't solved this yet. So it's kind of something we're thinking about. For example, here's a recent paper we had with some critical window modeling where we had time varying exposure across the pregnancy, but also we had multiple pollutants kind of interacting, and some of the interactions were more or less significant. They were changing over time in an auto-regressive way. So the point is, this part can get pretty complicated with lots of exposures in time, but also a number of exposures can increase, and so can their interactions. And so what happens to like a kernel density estimation approach, especially when we found it difficult to estimate like a multivariate version of this thing? Is there any way to kind of characterize that temporal smoothness at the least through this? So we're thinking about these problems now. We also have applied something similar recently to this paper. So again, I'm kind of spread thin as a biostatistician working here. So this was on clinical trial design, but the idea is really similar. So if you like this idea, then you probably will enjoy this paper too. But we adapted this model so that historical data from like a previously conducted trial can be incorporated rather seamlessly into a new trial that's being done, and you don't have to pretend like you have never seen results from a different population, for example. And so the method can dynamically like borrow more or less information, but it's built on a kernel density estimation prior that has this additional parameter that controls the level of like how peaked and how flat it can be. So the data try to inform about how much information from previous stuff is used. So the first author of this work was a student, Saskia Komis, who's fixing to graduate in next spring, Howard Chang at Emory, and we have support from the NIH. And here's the publication. We also have on my GitHub, we have an R package that for download if you want to use this. And if you have any trouble, just let me know. I'm the maintainer of it. So yeah, just let me know. And yeah, that's all I have for you today.
Before you ask the question, I just want to say that if someone online would like to ask a question, please raise your hand or type, and I will pass the question on because I think you are muted by default. But please feel free to let me know, and I'll pass your questions online.
So yeah, thank you very much for a nice talk. I was intrigued by your attitude to the multiple imputation approach, the cut distribution approach. I guess the advocates for that approach here would argue in your applied example that the number of stillbirths doesn't affect the PM 2.5. And I wondered whether you'd looked at how much the prior distribution for Z and the posterior distribution differ, and if so, if it differs a lot, are you happy with that?
It's a great question. Yeah, this is really getting back to the cut of feedback issue as well. Like, because you're right, as an output from this model that we have not mentioned is you actually get posterior distributions of Z, right? We have not looked at those. They were not interesting to us at the time until you've asked this question right here. If they changed a lot, would I be happy? Yeah, so this is really does the fact that the health information is informing about, I would say I would not be overly happy. No, I would not want it to change much conceptually. But I also, yeah, I need to check whether it's true, but I would be surprised if it changed a lot. I guess I just don't see how there could be much information contained in the health data about the exposure itself. But this is a really great question. We need to go back and look to see something we have not considered. But yeah, what would it mean, I guess? Changed. Yeah, and how much change is too much, I guess. There's a lot of questions, open questions at that point. Because even like the multivariate normal approach, I guess it would suggest there was change. Yeah, from like a multiple imputation, which yeah, I'll think about more about that. It must have changed significantly though, because discrete uniform also is kind of pulled towards the null here, right? Which would suggest, you're getting away from whatever's happening in one of the columns. It's not like one of these approaches is just selected a different column than this one. It must actually be selecting something that's not contained in the actual Z star. So there must be a shift. I don't know how to quantify what's too much and what would give me problems conceptually, but I'll think more about that. Thanks.
So, yeah, I was going to ask about the pull towards the null in the discrete uniform.
Yeah.
What do you think is going on there? Because naively, you would think that if you weight if all your posterior samples are IDD draws and you weight them uniformly, it would. Yeah. So why do you think it is doing that?
I think it's a function of how precise your exposure model is. So I kept thinking about this extreme case where your exposure model was perfect and every draw was exactly the same and was the true red Z, then it can flip through all of them and it's going to get the right answer every time. But if there's quite a bit of posterior predictive uncertainty in that exposure distribution, which there typically is, we're often not getting really tight posterior uncertainty there for those predictions, especially predictions in new locations and at new times. So the more uncertainty there, I think you just get a cloudy picture of what the exposure is. So none of them uniquely kind of jump out as dominant. So there's just a lot of, so we even tried upping the number of samples we keep to like 1 million so that we're cycling through more and perhaps, just the perfect ones lying out there waiting. But when you're actually calculating these kind of in the full conditional, it just jumps around a lot unless one is completely dominant and one is not going to be completely dominant. I guess. So, all right, we also tried a case where the discrete uniform was not forced to select just a column, but could select bits and pieces of all to form a hybrid one, but it still had to stick with the Z stars that were observed, but you could piece together from all columns. And that was a complete disaster. It was trying to overfit and the output made no sense at the time. So it got too flexible. And so, yeah, I guess my understanding at this point is that if there's too much posterior predictive uncertainty, you're going to have some jumping around, less than the multiple imputation, but more than you would probably like.
Does it ever happen that the posterior predictive distribution is multimodal? In which case, there definitely seems to be an advantage to your approach compared to the plugin or the.
Yeah, I'll say it happened infrequently enough that we didn't even consider it in the sim study because we felt like it would be cherry picking and kind of, we feel like clearly the new approach would dominate in that setting. So we could not find we went through our past modeling work and basically said because we do a lot of the exposure modeling ourselves, did we notice any of this bimodal or multimodal behavior? And we could not find any reference to it at all. So we didn't feel comfortable even simulating from it because it was almost cheating in our minds. So if it happens, it's great. All we could find are heavy tails, which is really an air pollution feature that happens a lot. But no, I have not seen it personally. But maybe with different exposures, I'm just dealing with kind of smooth air pollution. If you're dealing with like a heat wave type idea, you could certainly imagine a case where there's something modal going on, especially if you're kind of aggregating across time. The heat wave definitions right now they're varied, incredibly varied. So I can imagine there being some type of multiple modes going on there.
Thank you for the talk. Just wanted to ask, so in your parameterization of the negative binomial distribution, there is this additional parameter.
This R, yes. Is that the one you're the over dispersion parameter?
Yeah. So I think what is the prior for that? Is that a way to and
Yeah, so what we have done to allow for conjugacy was a discrete uniform on that. So we gave like 1 to 1,000. So it could be any of these. What I would say what's more common is what I've seen is like a gamma, just a gamma distribution, something larger than 0. But this allowed for computationally, the discrete uniform was a better fit here. But yeah, there's gamma is what I've seen most often, I would say. Yeah. But the logit, the logit link, doesn't change the interpretation of the parameters, which is what we like about this. It still has the nice, almost Poisson kind of feel to it, but you still get the over dispersion. With Poisson data, we always have this trouble with we had an observation level random effect to account for the over dispersion, and it looks like overfitting, and it becomes really highly parameterized. So we found that this is a little more stable from an MCMC standpoint to not include all of those random effects. So we've been sticking recently with the negative binomial.
Is that the fact that the logit gives you the same answer, is it because it's a rare event?
Say that again?
The fact that the logit gives you the same answer as, say, a log link, is that because it's a rare event? That's why you can interpret it as a relative risk.
Yeah, exactly. So if you write out what the expected mean of this logit with this formulation is, and you change the exposure by 1 unit and you kind of divide them, and you'll see that it comes out to be the same. The beta is there exponentiated. So it's the logit is, the log of P of 1 minus P. And so those logs kind of come together in a nice way. The only problem is it's the expected count is R times this exponential piece. So the R it shows up in it. That's the downside of it. So R has to converge well to make sense of the ratio. Yeah.
Can I ask, what is that 3 days lag? Seems a bit odd to me.
Yeah.
And I would have thought it was a kind of cumulative effect over that a period of time that really is driving the association with stillbirth.
Yep.
Did you look at a kind of like a weighted cumulative effect, or?
Yeah, we did not look cumulatively. And so this was also troubling to me. I would say looking at the population level is strange because people become pregnant at different times. So the cumulative loses a little bit of interpretation, like how long you've been pregnant versus me. So we have done an individual study on stillbirth where we're actually monitoring people's cumulative exposure individually. And that's actually in this paper here. And so we found like pregnancy week 2 and some closer to giving birth are important when you think in a cumulative fashion like this. But there's some disconnect to me between like this population level time series modeling and like an individual level study I couldn't square at the time.
just another one about the multiple imputation.
Yeah.
Like, is it intuitive that the width of the intervals is smaller than the plug-in estimator?
Yeah, I would say that's a good question. The way you pull all of the results at the end of multiple imputation is also we're using Rubin's rules, to kind of take the posterior mean estimates and the uncertainty and kind of pull them together into a. But it also happened with multiple imputation approximation, which let's see where that was. Yeah, so it's very similar. So this is literally in our MCMC, we're just cycling through different Z stars every iteration. I think the point is when it's towards the null, it's just towards the null consistently. And so maybe that's why there's a lack of, like here, I mean, you get I don't know, that's a good question. These two did really well when the truth was theta was equal to 0, right? It had the tightest uncertainty. And it was centered right at 0. So I don't know, maybe it's something about there's just literally no signal for each kind of cycle of Z star column, which means it's just a consistent answer of no, there's nothing, no association here. I have never thought of that though. Yeah.
Are there any questions online? Let me look at the chat. So I don't see any. So in that case, maybe we can thank Jeff again for